Okay, so we now have Zama Fest. We've got Sam and Damien are going to talk on parameter optimization for and larger precision for TFHE.
Hi everyone, thanks for having us. So I'm Damien, this is Sam, and we're gonna talk today about parameter optimization for TFHE. And we've done this work with Loris, Anas, Quentin, Ilaria, and Jean-Baptiste. Okay, so we're gonna introduce a bit the parameter optimization problem. Then we're gonna dive into it. So get ready. And we're gonna introduce this new algorithm that we propose in the Imprint paper, and we will conclude. Okay, so let's introduce. FHE, you all know what it is, right? But we're gonna go fast on that. You can do computation on homomorphic, you can do computation on encrypted data. So you can do additions, for instance, and multiplications. You all know that we have this noise problem. When it's too big, you lose the correctness.
Luckily, we have, it exists an algorithm that takes as input a ciphertext with a lot of noise and output a ciphertext with a lot less noise. And with TFHE, what's really nice is that for free, you can also compute a lookup table, a function on your message for free. So when looking at use cases at Zama, we noticed that there was some recurrent pattern in the computation graph. And so that's the pattern we came up with. So on the left, you see the private data in blue. You see some weights in black. And so you have a dot product, so that represents a level operation you can perform. And then you have a lookup table. So what's nice with this pattern is that you can rewrite any graph of computation with it and end up with a graph of atomic pattern. And this really simple pattern enable simple analysis, and you will be like, we are able to look at different ways to translate it into the FHE world. So the first translation we looked at is inspired by it is what we call the CGP atomic pattern. So now the private data is are LWE ciphertexts. So those are the one in blue with the little thermometer. The dot product can be performed over ciphertext. And to perform the lookup table, we can do a key switching and a programmable bootstrapping, which enable to compute the function and reduce the noise at the same time.
Okay, so now that we have those three homomorphic operators, we can have a look to the parameters, the FHE parameters. We distinguish between two classes, the macro ones and the micro ones. The macro they live longer than the micro ones. So we'll start from the beginning. On the left, you have the input LW ciphertexts. They come with an LW dimension n in, okay? Then we go through the dot product and we arrive to the key switch. At the key switch, there is a decomposition. So you're gonna have a number of levels, L in red, orange, I think, I don't, yeah. And you have also a decomposition basis, beta. So that's what's here. And at the end of the key switch, you end up with a smaller LWE ciphertext. The dimension is n small. Then you go through the bootstrapping. In the bootstrapping, there is again a decomposition. There are several of them, but they all share the same parameters, L, the number of levels, and beta for the base. And at the end of the bootstrapping, you have yet another LW dimension, N out. But N out is actually the result of a product between the GLWE dimension K prime and the polynomial size N prime. Those parameters are actually the parameters for the bootstrapping key. And N in is also following the same pattern because we consider that the input ciphertext are coming from bootstrapping. So here we have 9 parameters. And with those 9 parameters and the practical ranges for each of them, we end up with 2 to the power of 40 different possible parameter sets, which is a lot.
So let's look at this toy example. In here we have 3 atomic patterns. If we were to have independent parameters for every atomic pattern in the graph, we would have a search space of the size of 2 to the power of 120. So it's really big. So what we did is that we made like a common hypothesis in TFHE. So we assumed that we will be using 1 parameter set for the whole graph. And this enables us to have a search space that does not depend on the size of the graph.
So because we make this hypothesis, we have this, which is the noise at the end of the atomic pattern is the same, the exact same as the entrance of this atomic pattern. Okay, so we're gonna dive into the optimization of the TFHE parameters. We have 3 goals: security, correctness, and efficiency. For security, we needed a function f, and this function f was not available in the FHE ecosystem. So we had to do it. It was not us, but other people at Zama in the team. So they were using the lattice estimator. The lattice estimator, you know, I think, takes as input an LWE dimension, a ciphertext modulus, and a standard deviation for the noise, and it outputs the level of security that these parameters guarantee. So here we needed to turn things around, and we needed a function that takes as input the LWE dimension, the ciphertext modulus, and the level of security, and this function will output the minimal standard deviation that is needed to guarantee this level of security. So you're going to see in the next slide why it's fundamental to have this function. Then we have a second goal, correctness, and to guarantee that, we need a noise model, right? Because the noise is responsible for corrupting messages, so we need to have a good noise model to make sure that it doesn't happen. And finally, for the efficiency, we need a cost model, right? Because we're not gonna benchmark the 2 to the power of 40 parameter sets that are possible. We need something to help us compare parameter sets together without having to benchmark them.
So now that we have our 3 goals, we can introduce the optimization problem. So if we take a graph there, composed of several atomic patterns, we want to minimize the cost of the graph, which was one of our goals, such that at every step of the graph, the noise remains below some threshold that we call the noise bound. If the noise exceeds this threshold, the message would be corrupted. Of course, we cannot track the exact value of the noise inside the ciphertext. So we track the distribution of the noise, and so we can only guarantee that this inequality will be met up to a given probability that is given by the user. And regarding security, as we use the function that Damien just introduced, the minimal variance for encryption is a function of variable of the problem. So we don't need to care about security as it is by design. It will have a variance secure by design. So now we already introduced the CGP atomic pattern. Let's look at another atomic pattern and let's try to compare them. So for that, we use an algorithm inside the GBA paper. Just a word on coding. For the CGP atomic pattern, we had 1 message and we converted into we encrypted it into 1 ciphertext. For the GBA algorithm, for 1 message, you will have several chunks of data, and so you will have several ciphertexts. So for 1 message, you will have kappa ciphertext. And so we can define this new atomic pattern called the GBA atomic pattern with the 3 PBS allowing you to perform the lookup table. So this atomic pattern has the same capabilities as the CGP atomic patterns. And you can notice that the source space is a bit bigger because there's more parameters.
Okay, so we're gonna make a comparison between the CJP atomic pattern and the GBA. But first, we need to talk about the output noise of those two atomic patterns. If you look at the formula for CJP and the one for GBA, you have completely different noise formula. So at the end, you're going to have completely different noise. And also, in the three PBS in the GBA atomic pattern, you have more parameters. So it doesn't really make sense. So we need to find a way to compare them together in a way that makes sense. So we need to have them sharing the same exact context. So that's really fundamental. Okay. So here, that's what we do. We compare CJP and GBA. So by context, what do we mean? We, as you can see on top here, you have the log2 of the 2 norm. It's 6, and it's 6 for the three different instances that we consider here. On the x-axis, we have different precisions for the message. So as you can see, from 1 to 21. And on the y-axis, we have the cost. It's a logarithmic scale. Also, an important thing is the failure probability. Here, we have the same failure probability for the three instances, and it's 2 to the power of minus 35. What am I forgetting about the context? Okay, what can we see? First, a remark, CJP, it's basically TFHE, right? It's some dot product, a key switch, and a bootstrapping. And as you can see, it's not only binary messages in the ciphertext. It goes from 1 to 11 in this picture. So we're going to go by precision. Between 1 and 5, as we can see, CJP is the best option, right? Then, from 5 to 11, we can see that GBA is actually better, the 2 blocks version and the 3 block version. And at above 11 bits of precision, CJP cannot find any, does not offer any parameter sets. So that's good for GBA, I guess, because they are offering actually solutions for bigger precisions. Okay, so as an example, for a precision of 21 bits, we can see that the cost with a GBA 3 block, it's going to be the cost of here with a precision 5 times 2 to the power of 17, which is huge. And so what we would like to have is another option here in this area.
And so we came up with a new algorithm to evaluate the lookup table, combining non-building block in the literature. So regarding the encoding, it will be the same as GBA. So that means that for one message, we will have several ciphertexts. And so this is an high-level overview of the algorithm. So as input, you have kappa ciphertext representing your message. The first step you will do is bit extraction here. And so here you have ciphertext containing each bit of the message. Then you will do a circuit bootstrap, TFHE circuit bootstrap, to go from LWE ciphertext to GGSW ciphertext. And finally, you will evaluate several times the vertical packing to compute the lookup table. And so with this new PBS, we have a new atomic pattern with a lot more, like the search space is a bit bigger, but you have the same capability than CGP atomic pattern and GBA atomic pattern. So in the previous comparison, we were looking for something in this area, so something that scales better in precision. And this is a figure with 3 additional curves with this new bootstrapping. And what we see is that the purple curves, so for 2 and 4 blocks, are like where we wanted them to be. So it gives us an efficient alternative to GBA bootstrapping above 10 bits. And we also have more available precision. In here we have up to 24 bits of precision, but in fact it goes a bit more. and large precision are less costly. So earlier we saw that to compute a 21-bit PBS, it was 2 to the power of 17 times the cost of a 5-bit PBS. Here it's 2 to the power of 12. So we end up with a speed up of times 30. So if you look at the paper on Imprint, we have a lot of other results. So we came up with 3 encodings to build large integers with benchmarks and parameters. We also compared without padding PBS in the literature, so the LMP PBS with our own. We offer ways to deal with the failure probability at an atomic pattern level and at a graph level. We compared the key switch position, so comparing CGP and CGGI approach, key switch before or after the bootstrap. We studied how to optimally insert PBS in dot product, and we also looked at dealing with several key switching key and bootstrapping key.
So as future work, what we want is to improve our cost model. Indeed, in the experiments that we made, we used algorithmic complexities, so it could be nice to have something that is more accurate. We would like to have also a better cost model, better noise model, sorry, because when you have a tighter noise model, you end up with better parameters. As Sam mentioned, we started to work on having multiple key switching keys and bootstrapping keys in the same optimization, but it's something that is really non-trivial, so we would like to do better stuff on that. And finally, make more real-life comparison with graphs that are implementing some real-life use cases. Thank you very much, and if you have questions, don't hesitate. And also I want to say that we're going to update the print paper very soon, so you're going to see the up-to-date benchmarks and, I guess, better descriptions, and yeah.
Okay. Okay, any questions? Stunned silence. No? How far do you think it will go? So, you know, how far do you reckon you could push this? Just tweaking, you know. If you go back to your previous slide, I can, yeah. So ignoring, not the thank you, yeah, okay. No, the future work bit, the future work one. Oh, no, that one, no. I mean, I really meant the previous slide. I really meant that one, right. So ignoring the graph comparison for real use cases, you know, which is kind of, yeah. But with all the others, can you how much do you reckon you can push it? Are you going to get a tenfold, another tenfold improvement, another 100-fold improvement? How fast can you go?
It's difficult to say because yeah, we have some surprise every time so I don't really know. Like I mean, a better cost model. Obviously, we will have some nice speed up for free as soon as we have a good cost model, like fitted on the machine when we do the benchmark. For the noise model, we will not gain much. What can be really nice is to have something more generic to allow more degree of freedom in every algorithm, and with that, we can hope to have a speed up. For the multi-parameter set, it really depends on the use case, but in some experiments we made, we can opt like to have at least a factor 10 for some use cases. So yeah, that's the more important lead.
I think Sam mentioned it a bit, but for the better cost model, it would be nice to have a different cost model for every different architecture that we're working on, and it's going to be way better. And also for the multi-parameter set, it's really dependent on the use case. Because if you're working in a use case where you don't really need to have different parameter sets, you're not going to get a speed up right. So.
But if you had different cost models for each architecture, that would say that if you had a multi-user system, they would have to use the same. So you would, because multi-users aren't going to have the same architecture, so you would not really get the benefit there, yeah? Would that be right? It depends.
So I think in this case, the algorithmic complexity cost model can make sense because like it's a number of, like it's agnostic of the hardware behind, right? It's a number of operations.
So it's not hardware dependent, it's
Yeah.
not machine dependent,
Yeah.
it's
Yeah. So
okay.
yeah, we noticed that it's better to use the algorithmic complexity cost model than a fitted cost model on the wrong machine.
Yeah, that was my question. That's a better way of putting my question. Okay, any other questions? Okay, let's thank the speaker again. Speakers, sorry.